Unit 5, Truth Tables for Testing Validity. In Unit 3, we were concerned about determining the truth value of individual statements. So we used our truth tables to determine when a statement is true or false based upon the truth value of the components that are found in that statement. So if I had P and Q, in order to determine whether that statement P and Q is true, I had to know what the value of P was and what the value of Q was, and then I could find the value for that entire statement. What we're going to do in Unit 5 is sort of extend that idea, but apply it now to entire arguments. So rather than individual statements or individual premises, now what we want to know is, given a particular set of premises, do they lead to a particular conclusion? In other words, is it a valid argument? So when we talk about a valid argument, we've mentioned this before. A valid argument is one in which there is no possible substitution instance in which the premises are all true and the conclusion false. So for an argument to be valid, I have to have all true premises with a false conclusion. An invalid argument, on the other hand, is one in which it's possible for the premises to all be true and the conclusion false. So if I think of this in truth table terms, what I'm going to look for is an instance, a row in a truth table, in which each of the premises has a true value and the conclusion a false one. Now the way I can do this, or one way I do this, is simply to list all the possible values for each of the premises, all the possible substitution instances, and then look and see, is there any substitution? In other words, can I substitute in trues and falses for the P, Q, R, whatever? Can I substitute in those values? And if I get the right combination, is it possible for me to get all true premises with a false conclusion? So we're going to do this by, again, appealing to our truth tables, putting together all the possible substitution instances, and then look for that invalid instance. All right, so if I have a set of premises and a conclusion, and I want to know whether that's a valid argument, I'm going to try all the possible substitutions of T's and F's into that argument, and then I'm going to look for one substitution which has all true premises with the false conclusion. And so we're going to sort of, this is an extension then of the truth tables that we learned in Unit 3 and how to apply them now to full arguments. So let me just give you an example, and this may help clear up. When I look at the following problem, I've got not the quantity P or Q, R therefore P and not Q, and a conclusion not R. Now what I need to do in order to determine whether this is a valid argument is look for an instance in which this premise is true, this premise is true, and this one is false. If it's possible for me to pick T's and F's for P, Q, and R such that it ends up where the first premise is true, the second premise is true, and the conclusion false, then I know I have an invalid argument. So how I do this? Well, what I'm going to do is literally list all the different possibilities. So one way I could do it is to sort of pick these at random. So I could say, well, what if I made my P's true and my Q's false? So if I made Q false, and let's say I make R true as well. So I'm just picking a random value. So R is true, making not R false, which is exactly what I want. False, Q is false, which makes that true. P and that true and true. True, therefore true. So that's true. And I have true or false is true, making this false. Now in this case, I have a false premise here, a true premise here, and a false premise here. So that's just one possible substitution. Now notice, because I don't have all true premises and a false conclusion with this substitution, at this point, the argument still looks good. But that doesn't tell me, because notice that I just picked one possible substitution. There are other possible substitution instances, right? So in this case, I have to try them all to be certain that some other possible combination of trues and falses doesn't actually lead to an invalid argument. So in order to do that, what I do is go back and simply start listing all the possible substitutions. So if I were setting this problem up, and I'll show you how to do this yourself later, what I would do is say, well, I'm going to list all the possible substitutions. So here's what I'm doing here, simply listing all the possible substitution instances. And again, I'm still going to stay consistent here so that I'm sure I'm making the same substitution in each case. So there's that, and R is going to be true, true, false, true, false. So here now what I've done is essentially listed all the possible combinations. So P can be true, Q can be true, and R is true. And when I change that in, the question is that a valid or invalid argument? So now, once I've listed all the possible combinations of T's and F's, now I simply go through using my truth tables and find out what the value is for each of these expressions given that substitution instance. So first, I start with the P or Q. P or Q is true. True or true is true, making that false. True or true is true. Negate that, it's false. True or false is true. So again, false. True or false is true. And again, I know this just simply by looking at the truth table for the or statement. Then I negate that, and that's false. False or true is true. Negate it's false. False or true is true. Negate it, making false. False or false is false. Means that's true. And false or false is false. Negating that makes it true. Now what I now see is that this first row, this is the value for the expression for all the possible substitution instances, right? So there's for the first premise. Second premise, I would do the exact same thing. I go back and I look starting with what's in parentheses. Again, we did this in chapter 3, unit 3. P is true. Now, first thing I'm going to do is do the negation. So get that out of the way first. So Q is true. So all I have to do is flip this in each case. True, false, false, true, true. So that's just doing under the negation of Q. Now I'm going to do the conjunction. So true and false is false. True and false is false. True and true. True and true. False and false. False and false. False and true. And false and true again. So I've got here the values under the conjunction. Now again, working my way back out. R, therefore, and I'm going to look at what's under the conjunction. Right? I'm comparing these two columns now. True, therefore false is false. I know that false, therefore anything is going to be true. True, therefore true is true. False, therefore true is true. True, therefore false is false. False, therefore false is true. True, therefore true is true. And false, therefore true is true. Now again, if you know your truth tables really well, you'll note right away that the rows in which the antecedent is false, we already automatically know that it's true. So I don't actually have to refer to my truth table, if I have that memorized. So in this case, again, the final value for the truth table for all these substitutions, for this premise I should say, is what's under the horseshoe statement. So those are the values. And then finally, and this is pretty easy here, since the conclusion is just not R, all I have to do is negate here. So I have false, true, false, true, false, true, false, true. And that's the value for the conclusion for each substitution instance. So these are the three rows that I'm now, or three columns I should say, that I'm now going to compare. And I'm going to read across the rows to determine whether or not the argument is valid or invalid. So to do that, I look at each row, starting with, for example, here, we're going to look at this first row and go one by one, right? So each row I'll take a look all the way down to determine whether or not it's valid or invalid. So let's start with the first one. Well, already I know that for an argument to be invalid, I have to have all true premises and a false conclusion. So the first one already passes the test of as a valid row, right? Because I know that, well, that one isn't true. Same goes for here and here, all the way down. None of these are actually in consideration because each of them are false. So I have false premise. So for example, here I have a false premise, true conclusion. Well, again, do I have a situation with all true premises and a false conclusion? No. So I go to the next row. Well, immediately it's false. So I can pretty much ignore all of those now that have a false value in the premise. Now, when I get down to the second last row, see here I have a true premise. I have a true premise in the second, so R therefore P and not Q turns out is true for this substitution. And then I look at the conclusion, and sure enough, I have a false conclusion. So there is one row in their joint truth tables in which the premises are all true premise here, false conclusion. Therefore, the argument is, on this account, invalid. All right, so all I need is one row in which the premises are true and the conclusion false. And sure enough, when I substitute every value true falses in, I end up with true premises and a false conclusion. Now, how is it that I know I'm sure that I've hit all possible combinations of trues and falses? Well, in order to do that, there's a little formula that your book mentions, which helps you construct the base columns, right? So how many T's and F's do I have to try through? So imagine the following. I've got a problem in which I have P, Q, R, and S. So there are 4 distinct variables that I'm dealing with. So in order to determine the base column for something like this, for example, I use the formula 2 to the n, and n equals the number of distinct letters or variables. So depending on what you're working with. If you are determining the validity of an argument in which we're actually using English sentences translated, so the capital letters, you would use the number of distinct capital letters. In this case, we're using variables, so you want the number of distinct variables. And by distinct, I mean I'm not counting up, there's a P in this first one, a P here, P. So that's not 3, there's just one distinct letter. There's one P appears in the premises and the conclusion, Q appears in the premises or the conclusion, R and S. So 2 to the n, which would mean, in this case I have 1, 2, 3, 4, P, Q, R, and S. Those are the only letters that are used. So I have 2 to the 4th, and then you would just do math. 2 times 2 is 4, times 2 is 8, times 2 is 16. So what does that tell me? It tells me that I'm going to have 16 trues and falses. And half of those are going to be when I'm constructing my base column. So if I imagine I have P, Q, R, and S, and I want to know what I'm going to substitute in for each of those premises, what I'm going to do is have 8 trues and 8 falses all the way down. So I'm running out of room here, as you can see. And the same would be for Q. I'm going to have the same. I'm going to have 8 trues and 8 falses, except that when writing out that base column, half of those, we can think of those as half of those are going to be having the previous column. So I'll start with, if I start with 8 trues and 8 falses, then I'm going to have 4 trues and 4 falses in combination. And then 4 trues, 4 falses, 4 trues, all the way down 16. And then in the R column, I'll have true, true, false, false, true, true, false, false, and again, 16 until I hit 16. And then the final column will always be true, false, true, false. So this that I'm showing you here is simply a way of constructing the base column. In other words, these are what I will then substitute in will be these values across the rows. I'll just go row by row and substitute these in for each of the premises. So that's how I did in the previous example problem. What I did is I constructed a problem, since there were only 3 letters, so it was 2 to the n. So in the previous example, it was 2 to the 3, which means it was 8 rows. So that now tells me I have 8 rows. And you'll notice in the previous problem, so if you sort of scroll back and look at the way I created the base columns, when there's 8 rows, when there's 3 letters, and there's only 8 rows, the first row has 4 trues and 4 falses, and then it had 2 trues, 2 falses, 2 trues, 2 falses, until I hit 8, and then it was true, false, until I hit 8 rows. So that's the way we construct the base column. In some cases, the problems, as we get to this, normally you will not see 16 rows in something that you would use this method. Normally we restrict it to 3, but theoretically you can make a truth table up testing all possible combinations simply by using this 2 to the n formula. So if you have 5 letters or 6, that would increase, again, the number of rows that you need to test to make sure that the argument is in fact valid, or to ensure that it's not invalid. Depends on how you want to refer to it. So this is the formula. I look at the number of distinct letters. I take my 2 to the n. I say 2 to the n, replace the n with the number of letters, 4, and then I just do the math. That tells me I now have that number of rows. So in this first example I gave you here, it's 16 rows. If we look back at the previous problem that we just worked on, 2 to the n, there were 3 distinct letters, P, Q, and R. That meant there were 8 rows, and when you then construct the table, you start with 8 rows. Now, why half? I do 4 trues and 4 falses, for example, in the previous example, because it's a binary system. It's either going to be true or false, so it's one or the other. Half are true, half are false. The second row was half of the first, so I started with 4 trues and 4 falses. That made my 8. Then I had true, true, false, false, true, true, false, false, 8. And then true, false, true, false. So each, you can think of it as a case of each row is half of the previous row until you get to the last one where we just get to true, false, true, false. Now we'll see as I construct a few more of the example problems, you'll see how to create this base column. So let's do examples, some example problems. These are taken directly from the book. These are ones with answers that aren't in the back of your book. So PQ, in this case, I have a very simple problem. Imagine I want to know whether the following argument is valid. Now, in this case, for constructing my base row, 2 to the n, which equals, there's only P and Q, which means there's only 2 possible letters. 2 squared means I'm going to have 4 rows. So when I construct this, I can actually create, if I want to sort of off to the side, create a little cheat sheet here. I know that I have to have 4 rows, half are true and half are false, I would start out with. So true, true, false, false. And then true, false, true, false. So now I can just substitute those values in for the premises I have listed here, along with the conclusion. So P is true, Q is true, Q is true, P is true. And then the next one, P's are true, Q is false, Q is false, P is true. And this one, P is going to be false, Q is true, and P is false. And then the last row, they're all false. False, false, false. So you can see this column right here, or this little base column that I've made up here, it is not part of the problem that I'm comparing. That's just sort of my cheat sheet so I know what to substitute in for each of the premises in the conclusion in order to test for validity. Now, what's my next step? I have determined the base columns. I now go to my truth tables and I say, oh, this is a biconditional. So I go to my biconditional truth table. When both sides of the biconditional are the same, it's true. So both sides these are both true. There's true. True and false, they're different, so it's false. False and true, they're different, so it's false. And when they're the same, it's true. So in this instance now, I have these values for, these are all the possible combinations of trues and T's and F's, trues and falses that I can substitute in for the biconditional. This is already done, so I don't actually have to do anything with this other than say it's finished. And again, with the conclusion, it's also done. So in this instance, I have nothing more to do but compare these columns, right? So I have this premise, premise 1, premise 2, and then my conclusion. So I simply look across. Is there any row in their joint truth table in which the first one's true, or the premises are true and the conclusion false? Now, again, I can sort of simplify my work by noting that there are 2 instances in which the conclusion is true. Well, those don't count in the definition, right? So what I'm looking for is all true premises with and a false conclusion, or with a false conclusion. So I want to keep in that mind all the time when I'm looking at this, all true premises and a false conclusion. So I have false conclusion here. I look at my premises, false, true, false. Well, that passes the test, right? It's not all true premises and a false conclusion. My other possibility is here. This is false conclusion. I have true premise, but I have a false premise here. So true, false, false. That doesn't meet the definition, right? An invalid argument is one in which the premises are all true and the conclusion false. Well, there's no row in these joint truth tables. And notice here as you go across, there's no row in which I have all true premises and a false conclusion, which tells me that this particular argument is a valid argument. So let's try another one. In this instance, I've got P, Q, and R, so I've got 3 distinct letters. So if I start with P, Q, R, and again, I'm just going to review a little bit how to figure out that base column. So there's 3 distinct letters. So I know I'm going to have to substitute in for all those. How do I figure out how many rows? 2 to the third is 2 times 2 is 4 times 2 is 8. So that means I have 8 rows. And I know the first row will start out half true and half falses. So it'll be 4 trues and 4 falses. Then it'll be 2 trues and 2 falses, alternating back and forth. And then it will be 1 true and 1 false for the last row. So this is the formula. You can see that each of these, I go to 4 and 4, then I go to 2 and 2, then I go to 1, 1. Each of these is 1/2 of the previous row, right, as you move along. So again, 2 to the third, I have P, Q, and R. I know there has to be 8 rows down, and then each of those rows will be 1/2 of the previous row in terms of trues and falses. So I go here, I've got true, 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 false, 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 false. So there's the first one, right? 4 trues, 4 falses, that's 8 rows. The next row is going to be 1/2 of that. True, true, false, false, true, true, false, false. So notice, 2 trues, 2 falses in combination for 8 rows. And then the last row is always going to be true, false, true, false. Now again, once I've done this, now I simply go and transfer those values to each of these premises. All right, so in the first row, everything is true. True, 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 true. Next row, P and Q are true. R is false. R is false. P and Q are true. P and Q are each true. Then I have true, false, true. So P is true. Q is false. R is true. R is true. Q is false. Q is false. And P is still true. In this one, so I'm looking down 1, 2, 3, 4. Right? So I've got P is true. Q is false again, and R is false. R is false, Q is false, Q is false, P is true. And again, if this seems to get monotonous, well, yes it will, because as you get it down, this is a very mechanical way of determining whether an argument's valid or not. It's really just, once you've got the setup, copy in the values, refer to your truth tables, and there's not a whole lot of reasoning on your part. All you really have to do is keep in mind what the value of an invalid argument is. It's all true premises with a false conclusion. As long as you set everything up correctly, then the conclusion sort of presents itself to you without any real work on your part. So again, I'm just going to keep going through here and fill in the following values, the remaining values. P is false, so false, and Q and R are both true. So P is false, Q and R are true, R is true, Q is true, and P is false. Again, P is false again, false, Q is true, R is false, R is false, Q is true, and P is false. False, false, true. So P is false, Q is false, R is true, false, false, false. And the final row, everything's false. So false, 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 false all the way across. Now again, you don't have to copy those down. You could simply refer back and start working each of the problems. You don't necessarily have to write the base column out. If you remember your P, Q, and R, you can write these out directly into the premises themselves without, writing this whole thing over here first. Many people find, especially when you're starting out, you're still learning the truth tables, you're still getting used to how to set up that base column, find it easy to have this sort of little cheat sheet off to the side. And that's fine, whichever works for you. Now again, here it doesn't matter where you start. I'm just going to start from left to right. I know that P or Q, therefore not R. So first I'm going to do what's in parentheses. So I'll go all the way down. P or Q, true or true, true or true, true or false, true or false, false and true, false and true, false and false, false and false. Now again, I'm going through those quickly because I've got the truth table for the disjunction or the or statement memorized. All right, so if you're not seeing this as fast, just simply have those truth tables next to you, written on a sheet of paper, and follow along with that. Now I'm going to go to do the negation. So I have R, true, false, true, false. This is going to be easy enough. I'm just simply going to go and reverse the values. True, false, true, false, true, false, true, false, true. All right, so I simply written out the opposite, and now I compare. I'm looking at, remember, this is the value for under the or statement, and here the column for under the negation, which tells me the consequent. Now I go to my truth table for the horseshoe statement. Just remember here the main connective is the horseshoe statement. True, therefore false is false. True, therefore true. True, therefore false is false. True, therefore true. True, therefore false. True, therefore true. False, therefore false. And false, therefore true is going to be true. So now, if I want, we'll highlight here, this is all the possible values for that premise, right? I've done all the substitution instances there. Now I'll move over and do the same thing for the biconditional. This is the main connective, so let me start with the negation. Again, this one, it's true, true, false, false, so all I have to do is flip each of these. False, false, true, true, false, false, true, true. And then I've got true if and only if false. So that's false. They're different. They're the same. They're the same. They're different. They're different. False there if and only if false is true. True and true, and false and true. So now I've got the value under here. These are all the possible values. And go to my conclusion, which is just the horseshoe statement. So again, go to your truth table for the horseshoe. When the antecedent's true and the consequent is true, it's true. So true, therefore true. True, therefore true. I know that these are both true. False, therefore true, and false, therefore true. True, therefore false is false. True, therefore false is false. And those two are going to be true. Again, because I know that whenever the antecedent is true, it doesn't matter what the consequent is. I know the horseshoe statement is going to be true. So again, this is just reading off the truth table. So if I'm going quickly here, pause, look at what I've done. You'll see that it's just the truth table for the horseshoe statement. Now I look at my conclusion and I say, well, what is it that I'm looking for? I'm looking for all true premises, one row in their joint truth tables, right? So the main connective, one row in the joint truth table, and what the premises are all true and the conclusion false. Now in this case, there's really only two rows I need to focus on, right? The conclusion is only false for these two substitutions. So I look at this one, 1, 2, 3, 4, the fifth row down. So just making sure I've got it 1, 2, 3, 4, 5. I've got false, 1, 2, 3, 4, 5, false, and false. Well, this one I know, this particular row passes in terms of a valid argument because I don't have all true premises and a false conclusion. Now directly underneath it, I have a true premise, and oh, there's that false conclusion. So right here, I see that I now have an invalid argument. Right, this argument is invalid when P is false, true is Q is true, and R is false. Right, so that makes it invalid because there is one row in their joint truth table in which the premises are all true and the conclusion is false. So this is an invalid argument. Now here we have another much longer argument. Again, doesn't really matter how long, how many premises there are. It's all just plug in the values and look at your truth table. So as complicated as they are, as long as you're methodical, as I often tell students when I'm teaching this on campus, the thing that will actually help you the most when doing truth tables is actually having a ruler when you're writing these out, or at least lined paper so that you can keep everything in order. The biggest mistake students make, the problem they have when they don't get the answer correct, is usually not because they haven't read the truth table correctly. It's all about setup. They just simply didn't keep things in order in a straight line. Now in this case, because I have limited space here, I'm simply going to put the values directly underneath each of the premises here. All right, so I know that I have P, Q, and R. So there's 3 letters again. So again, just keep here, 2 to the third means 8 rows. And the first row for P, so again, I'm going to go in alphabetical order, P, Q, R. For P is going to be 4 trues and 4 falses. And the next row, Q, will be 2 trues and 2 falses, alternating until I get to the full 8. And then 1 true and 1 false for R, again, until I get 8 of the true, false. So this will just speed things up so I don't actually have to write out the sort of cheat sheet off to the side. I'm just going to put it directly in. So in this case, true, 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 false, 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 false. I'm just going to repeat this. Q is true, true, false, false. If you know that R is negated, then and that it's true, false, you can simply do the negation right off the bat when you're writing these in. So instead of writing true, false, and then negating it, I'm just simply going to write in the negation. And to keep it clear, it's always good to align your column so that the values are under the negation. So in this case, I'm simply going to go false, true, false, true, false, true, false, true, right? So I've done the negation instead of doing 2. This just saves you a little bit of time. In the case of Q, I'm going to do true, true, false, false again. So true, true, false, false, true, true, false, false. And again, you'll see there's a total of 8 as I go down. R in this case is just true, false, true, false. And then Q is true, true, false, false. And again, the important part is to try to keep these columns and these rows as even as possible. Here again, I have now a negated P. I could again write true, true, false, false, true, 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 false, 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 and so forth, but I'm just going to do the negation. So instead of 4 trues and 4 falses, under the negation, it's going to be 4 falses and 4 trues. And true, true, false, false again for Q. And now in this case, in this premise right here, I can't actually do the negation, right? Because this is a compound sentence. I actually have to do the Q's. I have to find out what's in the parentheses first. So in this case, I'm just simply going to do the true, true, false, false all the way down. Because in this case, also the negation here is the main connective of this expression. R is true, false. And finally, the conclusion, not R. So again, I'm going to do under the negation. Save myself a little bit of time. And then P is just 4 trues and 4 falses. Now, after all of that, the rest is, again, just sort of fill in the blank, right? So all I have to do is know my truth tables. Now, what's important, and this is why early on understanding what the main connective is, the value of each of these expressions is what's found under the main connective. So I want to know what the value of the first premise is, whether that's true or false, ultimately is determined by what's under that main connective, the biconditional. The or statement for the second premise, the negation is the main connective for the third premise, and the conditional statement, the horseshoe statement for the conclusion. So here again, working from the inside out, I start with what's in parentheses. In the first premise, P or Q. So I look at my or truth table. I know this is true, 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 false, false. And again, if you remember that the or statement is only false when both are false, it makes it very easy. The minute I see a T, I know immediately that that entire expression is true. So now I'm going to go on to the second part of the biconditional, the not R and Q. So in this case, it's a conjunction, and a conjunction I know is only true when both conjuncts are true, right? So when the left and right side are true, then I know it's true. And it's false in every other case. So if I see a false, I know automatically it's false. The entire expression is false, that is. If there's 2 trues, then I know it's true. So I'll just go down here again and put the values, false, true, false, 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 true, false, and false. And now I'm going to compare what's under the conjunction on the right side and what's under the disjunction of the or on the left side. So true if and only if false. Now remember with the biconditional, a biconditional operates something like an equal sign. It's true as long as both sides of the biconditional have the same value, right? Not that they're both true, but they have the same value. So if they're both true or they're both false, then the biconditional is true. So in the first part, I get true if and only if false. So I know that's false, true and if only if true, true and false is false, true and false, false again, true and false, true and true, false and false is true, and false and false. And now just to be clear, just going to put a little box over the final value for that expression. So those are all the possible values for that expression for every substitution instance. Now I go to the next part and I'm going to do just the same on each of these. So R if and only if Q, true, true, false, false, true, true, false, false, true. And again, I've already done the negation on the right hand side. So I've got that biconditional in parentheses to work. So false if and only if true. So I've got false, false, true, 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 false, and false. So again, now what's under that biconditional on the right side and what's under the biconditional on the left side, connected by the or statement, is what's going to determine the value for that entire expression. So true or false. And again, if you're, where am I getting these values? Again, go right back to your truth table. On the left side, I have true in this first row. and I have false over here. So true or false, go to your or statement, your or table. What is it when one side's true and the other side's false? It's true. So again, this is all plugging in directly based on what's on the truth tables. So I've got true or false, true, false or false, true or false, true and true, true and true, false and true, false and false, and true or false, which makes it true. And again, just so I can keep straight what I'm going to be comparing, I'm going to sort of box that out as well. This third premise, not the quantity Q or R. Remember, I do what's in parentheses first, and then the final value of that's going to be what's underneath the negation. So this is just an or statement, so this should be easy. Look at my truth table for the or statement. True or true, true or false, false or true, false or false, true, 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 false. And then this is easy enough because all I have to do is flip the value that I found underneath the or statement, what's in parentheses, and that gets me the final value for the entire expression. So this would be false, 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 true, false, 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 true. And again, just a good idea to make sure we keep clear what we're going to be comparing at the very end here. And now the conclusion. I've already done the negation for the or for the R, sorry. So it's not R, therefore P. I've done the negation already. False, therefore true is true. True, true, false, true, 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 false, false, true, false, 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 if and only false, if F, therefore F is going to be true, and true, therefore false is false. And since this is the main connective, I'm going to highlight that column as well. So now all I have to do in this instance is pick out where the conclusion is false. So I look at the rows. I have 1 here at the bottom and 2 up from there. So those are the only rows that matter, because remember, when we're looking for an invalid argument, or to determine whether an argument's invalid, we want to know, is it possible to have all true premises with a false conclusion? So all of the other premises up here don't actually matter to me, or all the other substitution instances, because those are true. So I'm looking for the instance where the conclusion is false. I then look across and say, is there an instance in which we have all true premises? So if I look at this bottom row, I notice that, in fact, the first premise, second premise, and third premise, all of these are true with the conclusion false. Therefore, I know that this is an invalid argument. And that's all I have to do. So again, the majority of the work involved in determining whether an argument is valid or invalid when using truth tables is the setup. Making sure that all my rows are straight, making sure that I'm looking at or counting in the negation, starting with what's in parentheses first, and then working my way out. So as long as I keep all of those things straight, coming up with the answer is fairly mechanical. But again, it does require that you understand how to apply the truth tables. You have to be able to identify the main connective, and you have to remember where to start in the proof, which again is starting from the inside, working from what's in parentheses and working your way out. So as long as you do the setup, the actual solution to the problems is actually fairly easy. The short truth table method. Now at this point, having worked several problems, you may be wondering if there's a quicker way of getting to the conclusion of whether or not an argument is valid or invalid. And there is another way that we do use to show the validity of an argument, and that's the short truth table method. Now there's another way we refer to this. It's sometimes referred to as the short truth table method. It's also the partial truth table method. And some just say the short method. So your book will use, I think, all 3 ways of referring to it. I usually call it the short truth table method or the short method. So the short truth table method is a way of focusing in on just the rows that may give us an invalid argument. So the core ideas are this. when we do a regular truth table, we insert every possible combination of trues and falses for each of the premises. So depending on how many possible combinations there are determined by our little formula, what we do is we go through and put every single one of those possibilities in there, and then we look and read across and say, is there any row in the joint truth table for each of the premises and conclusion in which the premises are true and the conclusion false? Now, this is fine if we only have 2 or 3, possibly 4 letters, but what happens when we actually get into larger premises or larger arguments that have more variables in them? Right, so if we think about what it takes to actually put together a table mathematically, we can see that our truth tables become really unmanageable the minute you get past a certain number of variables. So let's take a look. So if I have 2 variables, we know that 2 squared is 4. That's only 4 rows. Again, that's not particularly bad, right? So if I have true, true, false, false, and true, false, true, false, right? So I know that with 4 rows, I get a truth table that's pretty small. Now, if I go to 8, that still isn't too bad. So with 3 letters, P, Q, and R, 2 to the third is 8. In this case, I get 4 trues and 4 falses. And then true, true, false, false, true, true, false, false. And then my true, false, true, false. And notice, again, not bad, but still now things are starting to get along. Well, the minute I get to 4, where I've got 4 separate variables, now I've got 16. Right, in this case, I can't even write this on here because now I'd have 8 trues, 1, 2, 3, 4, 5, 6, 7, 8, and 8 falses. And you can see that this immediately becomes difficult to do. And if I end up with 5 or 6 separate variables, then it goes even crazier. So exponentially it grows the number of rows. So the question is, do we really need to substitute every possible combination of T's and F's in for all the premises? Or is there a way we could just focus on the 1 or 2 rows that we're looking for? Now, in fact, we only need 1 row. Right? So even if an argument has more than 1 valid instance, in other words, if I look across rows and find 2 in which, row 3 has all true premises and a false conclusion, and row 6 has all true premises and a false conclusion, that's fine, but I don't even need to go as far as 6. Once I find 1 invalidating instance, that's all I need. So really, we can shorten things down if only we could focus on just those rows in which the conclusion is false and the premises are all true. So what the short method does is actually have us focus in on just those rows. And how we're going to do it is by sort of creating those rows ourselves. So what we do when we do the short method is, rather than plugging in all the possible combinations, we start with the conclusion and try to determine which substitutions would make it false. So I start with the conclusion, say if I want to know if it's possible for there to be all true premises and a false conclusion, well, the first thing I do is pick T's and F's such that the conclusion is made false. Then whatever values I pick for that conclusion, I have to put those into whatever premises. So if I have a conclusion, which is just something simple like P therefore Q, and I know that P is true and Q is false, then what I have to do now is substitute in those values for any P or Q that show up in any of the premises, right? So I have to be consistent. If I make P and Q true, if I make P true and Q false in the conclusion, then anytime I see a P or Q in that same row, it also has to be that the P's are true and the Q's are false. Then what I do is go through and attempt to make all the premises true. So now I've made my conclusion false. I've transferred the values, the T's and F's for whatever I needed to make my conclusion false into the premises. Whatever's left over, I now attempt to make true. So I make the conclusion false and try to make the premises true. When I say try to make it true, I'll show you as we do some examples why that may or may not be possible. So I then select values that make the premises true while the conclusion is false. If I'm not able to choose values for the variables that make them true, while keeping the conclusion false, then it is a valid argument. Obviously, then if it's possible to make the conclusion false, transfer those values and pick other values for the other letters that make the premises true, then it's an invalid argument. So I think an example will help sort of clear up how this works. So here I have a very simple example, one we had before. In this case, I start with the conclusion. So the first thing I want to do is say, rather than writing out all the possible combinations, so in this case it would simply be 2 to the third or 8 rows, rather than writing out 8 rows, is it possible for me just to create that one row which might be invalid? So the first thing I would do is go to the conclusion. And again, seeing that I have a nice simple horseshoe statement. When is a horseshoe statement false? When the antecedent is true and the consequent is false. So now I have true, therefore false is false. So Q is true. So if I wanted to even, I can in fact even write over here, Q is going to be true. And anytime I see a P, I'm going to make that false. So in this case, I've got 3 letters, so I already know 2 of them. Q is true. P is false. Q is true. And that's it. So I'm done with transferring my values over. Now my goal is, since I've got my conclusion false, is to try to make each of these premises under the main connective true. Right, so I have to pick values that'll make it true. So let's start with the biconditional here. I've got Q is true, not Q is false. Now if I look at my truth table for the biconditional, I know the only way to make a biconditional true is if both sides have the same exact value. Now Q is fixed. I can't do anything about that. I need Q to be true to keep the conclusion false. So Q is true, not Q is false. Therefore, R must be false, right? Because R has to have the same value as not Q in order for this whole expression to be true. So now I've made that premise true. Now, since I've picked R as false, and it has to be false in order for this premise over here to remain true, I have to transfer that value over to the first premise. So R is false, not R is true. Now I just do what I would normally do with determining the value of an expression. So for the first premise here, I say false or true is true. True, therefore true, is true. So I have true premise, false conclusion. This is an invalid argument. So what this does is really just narrow down, rather than doing all of those possible substitutions. What I'm actually trying to do is see if I can recreate an invalidating instance. Now it is possible that when I do this, it doesn't come up as an invalid argument. So you can imagine I have a very similar problem. Let's say I've got the same conclusion. And let's say this second premise, there's no negation on the Q. And then I have my first premise, P or Q, therefore not R. Now the P and Q remain the same, right? I still need Q to be true, P to be false. I transfer those values over. So Q is true over here. Q is true, P is false. Now again, if I go to the biconditional here, and I say, well, if Q is true, then R must be true in order to make this true. So I've made one of the premises true. But now R has to be true. R becomes true, and I can't pick anything else. Not R becomes false. P or Q, false or true, is true. True, therefore false, is false. Now notice in this instance, this variation on the problem, false, true, false, means that this is a valid argument. So this is what I mean by it's impossible to make the premises true with the conclusion false. Q is fixed in order to keep the conclusion false, right? Q has to be true. P has to be false. Otherwise, I couldn't make that conclusion false. Therefore, when I substitute those values into the other premises, there's nothing I can get but a valid argument. And there's no other possible combination. So notice the conclusion is only made false one way, when Q is true and P is false. Now in other problems, there might be more than one way to make the conclusion false, which means you will have to test each of those substitutions. So if there is another way to make it false, then you have to go through the process of trying each of those instances. But notice, instead of trying 8 rows, I only had to do 1 row, right? So that, again, is a time save right there, even in a problem that's as short as this one, with as few variables as this one. So what I want to do now is just go over some more examples of the short method, just to get you comfortable. Again, the short method does require that you really know your truth tables sort of inside and out at this point. All right, so doing the long truth table method helps you to learn the truth tables, to be able to remember them, to memorize them. It's very helpful to memorize. So while I encourage you to keep them written out on a piece of paper next to you as you do the problems, it's also very helpful to work the long method, if for no other reason than you start to see the values and the relations, that you don't have to constantly look at, sort of a cheat sheet on the side for yourself. So let's do a few more of these examples so you get sort of comfortable doing the short method. So you can see here we have a much longer problem, P, Q, R, and S. So in this case, there's 4 variables. If we had to do 2 to the 4th, 2 times 2 is 4, times 2 is 8, times 2 is 16. It would be 16 rows, and you'd have to do, plug in all of those 16 rows, look across, see if you find the invalidating instance. Here, though, we might find that it's easier way to do it. All right, so the first thing I do is go to the conclusion, and I attempt to make the conclusion false. So how do I make this false? Well, that means the antecedent has to be true and the consequent false. So how do I make the antecedent true? Well, this is actually pretty easy because there's only one way to do that. To make a conjunction true, both conjuncts have to be true. So S has to be true and P has to be true. So if I want, I can sort of mark off to the side just so I remember. I'm making S true and I'm making P true as well. Now I have a P in the consequent. And again, the consequent now I want to make false. So my antecedent is true. I want this whole thing to be false, which means it has to be false under the negation, right? So what's in parentheses has to be true. What's with the negation has to be false. Now P is already set because I need P to be true in the antecedent. That means P here has to be true, which means Q can be either true, it can be false. Right, so those are the only possible combinations. P must be true, so notice that constrains me there. So in one case I have true or true is true, making the negation false, making the conclusion false. In the other instance I get the same thing. True or false is true, negated is false. So now I have 2 possible combinations to check. The first row makes Q true. So if I look down here first time around, I say Q is going to be true. And I substitute those into my premises. So I'll try this. I'm going to test the first one, see if I can make that an invalidating instance. So I'm just going to go through. S is true. S is true. P is true. And I know Q is true. Right? So those are just the values I've picked in this first row to make it invalid. Now it doesn't actually matter where you start. Again, now that the conclusion's false, the object is to make each of these premises under the main connective true, right? That's my goal, is to make those true. So if I start with the first premise, P or Q, true or true is true, which means I don't want this second section to be false. Now in this case, R can be either true or false. It doesn't actually matter. So again, knowing your truth tables, and this is where it's important in the short truth table method, I know that R or S, that I want to be true. It just can't be false. S is fixed. So if I make R true, it's true. If I make R false, it's true. And that gets me the whole. Now the reason I do this is because I might, when I get to another premise, say premise 2 here, I might want to make R true. I might want to make it false. I'm not sure which I want to choose yet. So I use this as sort of a placeholder and say, well, it doesn't really matter what I choose for R. I can come back later and sort of formally assign it a value. But now I get to the biconditional. I have P is true. R and S in parentheses have to be false. in order to get the negation of that, what's in parentheses, true. So let me say that again. This is a biconditional. I know to make a biconditional true, both sides of the conditional have to have the same value. We already know that P is true, which means that everything on the right side also has to end up true. Because I have the negation outside of the parentheses, what's in parentheses has to be false so that when I negate it, it becomes true. So S is true, that's fixed. The only way to make what's in parentheses false so that I can negate it and switch it back to true is to make R false. So false or true is false. When I negate it, I get true. True if and only if true is true. Now what that means is I can come back over here now and say, oh, what I really meant to say was that R is false. All right, and so I can go in there. If I want to, you can erase. Again, it doesn't really matter. At the end of the day, the whole point was to simply say, or attempt to find out whether you could make the entire premise true. But there we go. We now know that R is false. So if I want to again, I might write that off to side to remind myself that wherever I see an R, it has to be false. So now I go to the last premise, the only one I haven't done yet. So already I've got one true premise here, one true premise here. So the question, can I do it for this last one? Q is true. So again, I need everything on the right side to be true. R is false. True or false, or true and false is false. Negated is true, making this whole thing true. And look at that. First time out, I have true premise, true premise, true premise, and a false conclusion. So this is an invalid argument. So again, you can see that this saves a lot of time. Now, if it was the case that I had done the substitution in the first instance and I didn't get all true premises and a false conclusion, I would still have to check this second instance. Just because it passes the first test, that's one instance in which the conclusion is false. Note there's another possibility, right? So I can have S is true, P is true, and Q is false as my starting point. But I didn't need to actually do that because I found an invalidating instance. So once you find an invalid row, using the short method, you don't have to test the other ones. So again, depending on what the conclusion is, you can have 1, 2, 3, even 4 different possible combinations. The minute you hit one that's invalid, you can stop testing. You don't have to do all of them. And that also goes for homework assignments or exams. You don't have to show me that you can test all of them. The whole point of the short truth table or the partial truth table method is to speed up your ability to analyze arguments and determine whether they're valid or invalid. So to take another example here, we've got 3 premises, P, Q, R, S, T, and W. So P, Q, R, S, T, W. That's 6 different possibilities. Again, the short method, done the same way though. It doesn't matter how many different variables I have. First thing I do is look at the conclusion and attempt to make it false and keep reminding myself that I want to make each of these premises true under their main connective. Well, it's a horseshoe statement. That's nice. I want to make the consequent, going to start there, P or S, means I want to make that true. Well, this means, and you can notice, both can be true, true, false, false, true. So in this case, there's 3 possible combinations which will keep that antecedent true. Now I look at the consequent. I want to make the consequent false, which means that what's in parentheses here, the R and T, right? In that case, I want to make that true, so the negation is false. Well, this makes it nice and easy, right? Because in this case, the only way I'm going to make this true is if I keep them true in each instance. So R and T are true. When I negate that, I get false. And again, if you're not seeing this, why is it that R and T must be true? Because that's the only way a conjunction is true, is when both conjuncts are true, right? And because I have to negate it for false to make the horseshoe statement false, I know that R and T are going to be fixed. And in that instance, or with that, I now have false, false, false for my conclusion. Now here again, I now just have to test all the various possible combinations. So again, there's 3 in this instance, but that's still shorter than had I gone and done the 2 to the 6 and tried to find all those possible combinations. So again, it's up to you. If you like reading off sort of the conclusions that you made up, you can write off to the side if you want. Sometimes that's helpful. So if I wanted to say I'm going to try the first row, and I might say P is true, S is true, R is true, and T is true. So this one, everything's true, which makes filling in pretty easy. So I know P is true. Now R here is true, but the negation makes it false. So I'm going to go right and put down false under the negation just to save myself time. Q I don't know yet, so I haven't picked, right? I have P, S, R, and T. S is true. T, again, with not T, T is true, so not T is false. And I still haven't picked a value for W, or not W. So here I'm going to go through, and I know that if I want to make this first premise true, and I have a consequent that's false, then I have to look at my truth table and say, well, in what situations can the consequent be false in the horseshoe statement while the whole expression still being true? Well, what that means is this antecedent over here must be false. But notice that's impossible, right? Because the minute I have P is true, doesn't matter whether Q is true or false. If it's true, it's true. If it's false, T or F is still true, which still gets me false over here. So I already know that there's no way in which this first row is going to work. As long as P is true, then I've got a problem. I've got an OR statement here, and so that's not going to work for me. Now, what this also tells me is that because I know there's a problem that P must be false, that I'm going to need this, again, R is a fixed quantity. I can't change R. R has to be true so that not R and not R becomes false, right? And I know that R has to be true because it's in the consequent. The only way to make that consequent false is to make sure that R remains true. It has to be in every instance. All right, so notice the row here. So what do I do? Well, in this case, the next substitution also has P as true. Well, I already know that that's not going to work for me. Now, if you didn't see that, that's fine. If you weren't looking at it, you weren't thinking in those terms, it's fine. You just go on to the next row, test those possibilities. But to save a little time, I'm going to go, wait a minute, here's a case where P is false. So now, if I go to this last row, I have P being false. S is still true. R is true. And T is true. All right, so now I'm going to try those possibilities. And again, I know this because I'm looking at R as being fixed over here. So just looking at and understanding what makes that first premise true helps me to pick which one to test next. Again, if you don't see it, that's just fine. It's not that difficult to do all 3 possibilities. So I look here, and I've got now P is false. Q is open still. Right, but I know what Q is going to be. Q is going to be false. False or false is false. False, therefore false, gets me true. So now I've made that first premise true. Now in the second one, S is still true. Right, so again, I'm using this set of substitutions now. S is true. Not T. T is true. Not T is false. And lo and behold, look, there's nothing I can do. It doesn't matter what the value of W is, right? So true, therefore I have a conjunction. Since this whole thing is false, it doesn't matter whether that's true or false. It's going to be false. True, therefore false is going to be false. And therefore it's impossible for me to get all true premises with a false conclusion. Now, if you're not sure, I can look at this, again, that second row that I told you we can sort of ignore. You notice that S is false, and S being false here would actually make this true, but also because P is still true, that would still make that false. So in this case, even doing that second row, what you're going to find is that you're simply switching which of the 2 premises are true and which is false. All right, so in this instance, I now know that it's impossible for all the premises to be true with the conclusion false, and it's a valid argument. Now again, what's important here is to recognize that I was able to do this with at most doing 3 rows, doing 3 substitutions. The difficulty is that you really do have to understand the truth table and be able to sort of think in reverse, right? So when I look at these problems, when I look at these premises, I have to be able to judge, okay, what am I going to, not ultimately what am I going to need at this second, but what happens when I negate that, right? So thinking ahead. So let me, just to give you, to make this more clear, when I'm analyzing a statement like this second premise, right, I have to know, one, what makes a horseshoe statement true and what makes it false. And so I have to keep that in mind. 2, I have to look and say, when I'm given a set of values, so when S is true and when T is true, then I say, okay, now how do I make this whole thing, this whole expression true? Well, the minute I have a true in the antecedent, I have to know from my truth tables that this whole piece over here has to be true as well. Right? So now I'm thinking a little bit differently. I'm trying to create the thing that I need. To make this whole thing true, I already know that I've got a problem, right? So I've got a conjunction in here and both conjuncts have to be true, but that's impossible. I can't do that. And so immediately I know that that substitution doesn't work. But notice the analysis I have to do. I have to think of, this is fixed. This is true over here, so this must be true because I know my truth tables. I know that the horseshoe truth table, if the left side is true, the right side is automatically going to have to be true if I want to make the entire expression, this entire thing, true. So again, this is where the short truth table method really means you have to understand how the truth tables are working. It also is very important that you recognize what the main connective is and what any sort of subconnectives, that you follow the order of operations, that you do what's in parentheses first. When you have negations, you have to make sure you change the letters. In this case, something like not T or not W. You have to make sure that you negate those before you do the conjunction working from the inside out, before you get to the main connective on the outside. But once you've got that, it does save a lot of time. So the short truth table method is one where, one, it really demonstrates whether you understand the truth tables, you understand what they're saying, but it also can save you a whole lot of time.